Okay, so theorem 1.47, here's the theorem statement. The class set of regular languages closed under the concatenation operation. Okay, so we just, theorem statement's the same except for this one word. So the operator we're using now is like little circle, the concatenator. Okay? I assume you understand what that means because we've done it quite a bit. Alright, so again, proof idea. So as usual, so we have two languages, any two languages that belong to this class of regular languages, A1, A2, just any two. And we're now trying to prove that the concatenation, which is represented here by this little circle, okay. Well, maybe we'll revise just a little bit. So, what is this? It's a language, and we have to show that it's a regular language. That's what we're trying to prove. In other words, we have to construct. It's a proof again, a proof by construction. We have to find a machine, find an automaton, in this case an NFA, that recognizes this. And what is this? What is this language? It's the set of all concatenations of the form XY, where X would be a string from this language and Y is a string from that language. Okay? That's all it is. So it's just, this is the language of all possible XYs, where the X and the Y concatenated, joined together. Right? X, Y. Alright, so we have to prove that that's regular. So we have to construct a machine, big N again, that recognizes this language. Okay? So the basic idea, so again we take two NFAs, N1 and N2 as before, okay? But we combine them differently because this time we're talking about concatenation, not the union. So the way these two NFAs, these two components, these two parts, if you like, N1 and N2, the way they get combined is different. That's probably not surprising. Okay. All right. Now here's a few other essential ideas for this proof. This second proof here's a new one. So make big N, make its start state the same as N1's start state. Okay. Now, why is that? Does that seem plausible? Remember, you're trying to detect. But you've got a concatenation. It's like here's your X string and here's your Y string. So you have to detect. So big N, if it detects an X and then a Y, it has to start with the X, right? So it makes sense to start big N, have its start state in the same start state as N1, because N1 is doing its job first. So it has to accept the string X, that it belongs to. The string X it has to detect that it belongs to language A1, right? And then we want machine N2 to detect the string Y that belongs to language A2, right? So it's like two jobs, but consecutive. They're not going on in parallel; they're one after the other, in a sense. So first accept string X, and then accept string Y. Right. Okay. So have big N have its start state be equal to the start state of N1. That seems reasonable. All right. And then and here's another essential idea: creative thinking. Have eta arrows pointing from the accept states of N1, and have them pointing to the start state of N2. Okay, that's a critical and creative idea. Does it seem plausible to you? Right. Now here's, in terms of the diagram, here's what's going on. missed something? Let me check. I think these should be accept states. I've forgotten. Well, I'll put here. Look, I'll put a sort of a dot around them. So, now in the textbook, there is not a double circle here or here. I just have single circles because we talk. I guess because we're talking about big N, and these. We had. Oh, debatable. Okay, so here's like another essential idea, right? So these circles here represent the accept states of machine N1. This is N1, this is machine N2. And then if we get into an accept state for machine N1, in other words, machine N1 has accepted the string, the X part, right? And then with the eta arrow, it immediately goes to the start state of N2, okay? And then starts seeing if the next series of input symbols corresponds to the Y, to a Y, a string of language A2. Right? So that sort of seems reasonable. Okay. I think that's what I've been saying in words, right? Right. So you start. Oh, I've forgotten the start symbol. Okay, so you start in the for big N, the whole thing with these two parts. You start. N start state is the same as the start state of N1, and then hopefully you're looking for X, where X is a string belonging to language A1, right? So assume you find it, and then you get to you get to an accept state in N1, and then with the eta arrow immediately go to the start state then of N2. You're looking now for the Y part in your concatenated XY using N2, right? And then if you end up in the start an accept state in N2, that means your machine N2 has detected the Y part of your concatenated string XY. Okay, and if that's the case, and that's the end of the string. You've read the last symbol in the input string, then N2 would accept, and if N2 accepts, well, N accepts, right? And we'll do that when we do the formal model of N. We will say that if N2 accepts, then N accepts. And why is that? Well, if N2 accepts, it means it's found Y. But you could only find Y if it's all previously found X. So if N2 accepts, that means that N, the big one, has found XY, the concatenated two strings, the X string and the Y string, concatenated XY. Right? Okay, so now let's find the formal specification of this machine N. Okay. So again, we'll use two parts, two NFAs, N1 and N2. So here are the two 5 tuples for the two machines. Again, to simplify things a bit, we assume the same alphabet for both machines, for both NFAs. Okay, and it's a proof by construction. We have to construct a machine. An NFA, and here's its formal specification. Okay. Right. I don't know why. Oh, it's just distinguished. Okay, just calling it Q. Well, this is distinct from Q1 and Q2, and the delta is distinct from delta 1 and delta 2. Right. Oh, I see. Okay, now look at this. Look at this F2 here. Now that's made explicit what I was saying a bit before in words. So the set of accept states for the big machine will be equal to the set of accept states for N2. Remember me saying that? So your big F here will be F2. In other words, equal to this. And that's the set of accept states for a machine N2. Because if N2 accepts, that means that N has seen X and Y. Because you can't get N2 moving until X has been accepted. Right? Okay. Now, so what's Q? Well, it'll just be just the union of the two sets of states, right? It'll just be the union of Q1, Q2. There aren't any other states. There's no extra. There's nothing. No, you can't see it. There's no extra states put in. So it's just the union of these two. That seems fairly obvious. Okay. The start state of N is the start state of N1. So that's where this Q1 comes from. Okay. So that's the start state of N1. Here it is here. Okay. So you start here. So that Q1 is the same as this one here, and that's the start state of N1. All right. Now the accept states of N, the big one, are these, but they are the accept states of N2. So F2 here has to be the same as the F here, F2. So these two have to be the same. All right. Now. Again, the devil in the details. Usually the hardest part is specifying formally the delta function, the delta, the transition function. But that's next session, so I'll just go straight on once I've moved the camera.